So let's recall that logistic regression uses a similar form of a regular multiple regression, but the outcome variable is binary, that is 1 or 0. And the logistic regression model relates the probability a resume here. There's a specific example. I'm getting this from the textbook. And oops. So resume, meaning dependent variable would receive a callback. That it means it would be 1 to the predictors, x, the predictive variables through a framework, much like that of multiple regression. So it's just the same idea, except that what the logistic regression model does is build a kind of probability model. So the y, it doesn't predict, it doesn't attempt to predict the y, it predicts the probability of the y. And it does this by using the log, by getting, it returns the log of the odds ratio, which is the probability 1 minus probability. So that's the transformation over here. So when we have the data for the logistic regression, we've got the actual y. So let's say, resume callback 1 or 0, and that's 1, 0, 1, and then we have the predictive variables. And these can be numbers, this can be like other binary variables, yes or no. Like the idea here is does the race of the person predict if they're going to get a resume callback or not? And so things like that, what is their GPA or whatever. And so on the data itself, the outcome variable, we only have one, is binary, 1 or 0. But once we build the model, sort of in the multiple regression, this would be y hat, or the predicted y. It predicts a log of the odds ratio. Okay, so this is more of a probability. So it's not going to predict a 1 or 0. Predicts more like a odds ratio, but a probability. So a ratio, like 3 in 5, or 1 in 7, something like that. So that's kind of what is important to remember. So we have several model conditions in logistic regression, just like we did in linear regression, but it's slightly different. So we still want the observations to be independent. We also don't want multicollinearity among the explanatory variables. We want to make sure we don't have extreme outliers and some of the data looks normally distributed. We want also this linear relationship between the explanatory variable and the outcome variable, but the logit of the response variable. So here we want a linear relationship between the explanatory variables and this here, the logit. Here's, the logit of the outcome variable. Okay, and then the data set is large enough. So observations are independent. So this is kind of straightforward. So let's say we have data on bankruptcy. Each record is a person, and they have had or not had bankruptcy in the past. And we have all the information about these people, their income, credit utilization, etc. And what this observations are independent means is that when we collected this data, there wasn't any sort of relationship between the people that we selected. So each person is not related to the bankruptcy of another person. So we didn't just, for example, went to some area of town where they have a lot of people with bankruptcy and just included those guys in their observation. So we want independent observations from each other. And this is the same case in multiple regression. No multicollinearity among explanatory variables. This is the same, and we can do a correlation matrix of predictive variables if they are numeric. We can also do a tabulation of counts to kind of see if some of the we see some collinearity among certain of the variables there for the categorical ones. We want to avoid extreme outliers, so we can check this with box plot or histograms of the explanatory variables. Also, this is the tricky one, which is there is no a linear relationship between the explanatory variables and the logit of the response variables. In the case with the multiple regression, we can just create a scatter plot, but here it's a bit tricky to do it. There is a test called Box-Tidwell test, and I think this is available in SPSS. There must be a Python package for it. I haven't used it, but I actually have not done this test before. I just know that this is a condition, and sometimes, some people, if they're really picking in your model, they're going to be like, hey, did you even check if there's a linear relationship? But there might be ways to do it. So for example, if you do get the logit, remember, we get the logit of the outcome variable. So these are numbers more like this, or these are more like probabilities, right? So it's not just 0 or 1. Because if it's 0 or 1, it's a little bit tricky to graph. So you just have 1 or 0, so all the values are going to be here or here, so it's kind of hard to see linearity. But if you are 0.5, 0.8, 1, if you have working with the logit, then you might be able to see a linear relationship. So there might be a way to create actually a scatter plot between the numeric predictor variables and that logit variable itself. I probably won't ask you to do this, but I wanted you to keep this in mind. And lastly, we want to make sure the data set is large enough, and as a rule of thumb, we want this kind of like a 15 to 1, this 15 to 1 rule. So we want 15 events for every parameter, so at least 15 records for each individual value. So 0 and 1, we want to have at least 15 on each side, and for each explanatory variable that you have in your model. So if there are 3 explanatory variables, each of the response category will have at least 30 records, that is 15, 15 a yes and 15 no, times 3, so that's about 90 records for a model with 3 explanatory variables. So that's about some of the model conditions of logistic regression. That's it for this one. I'll see you next time.